All right. So this is signals and systems, and this is the this is lecture number 19. And today is the makeup class because we had a technical difficulty last time on Thursday, and we needed to cancel the class. So today is on Saturday, 16th March. The time's about 10:30. I'm sorry. The time's about uh 10 to 12 in the morning. And I appreciate you coming today because this is Saturday. Okay. So last time we were talking in the lecture and about how to find the inverse Laplace transform, how to find x of t, which is the inverse Laplace transform of xs, given the Laplace transform of xs in the form xs equal to k s minus z1 s minus z2 all the way through s minus zm divided by s minus p1 s minus p2 all the way through s minus pn. Okay, be careful here. M and n are probably two different numbers, and m represents the order of the numerator. Okay, so m is the degree of the numerator, and n is the degree of the denominator. In general, the k is a real number called the gain of xs. Z1 through Zm are complex numbers. By saying complex numbers, they could be real numbers, but in general, they could be complex or real numbers. Okay, and these numbers are called zeros. And P1 through Pn are also complex numbers called the poles. In general, the behavior of xt is almost always described by the character of the poles. Okay, we will consider three cases. We considered three cases. First, poles are distinct. This is the easiest case. All poles are distinct. Second is there are repeated poles. And third, there are complex poles. You see that the behavior of xt here depends on each of the cases. For example, if all the poles are distinct, then xt is represented by a particular form. But if there are poles that are repeated, then the form of xt will be different. And if the poles are complex, then the form of xt will be completely different. There will be some oscillation going on, as you will see. Now, for distinct poles, all poles are distinct poles. Okay, we can write xs as k1 divided by s minus p1. By distinct pole, I mean p1 through pn are not the same, are distinct. Not two are identical, so they are all distinct. So when all the poles are distinct, I can write xs in the following form: s minus p2 plus blah 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 all the way through kn s minus pn. Okay, so these are each of the poles. Okay, these are each of the poles. The number of the terms here is equal to the number of poles. Okay, so number of terms is the number of poles. For example, if you have 4 distinct poles, then there will be 4 terms added together. Okay, and k1 through kn are constant, and they could be complex numbers. Okay, but we will leave the case where the case are complex numbers to the third case. In this case, in the first case, we will assume all the case are real numbers, but we assume first that all the k are real numbers. We will leave the case where some k's are complex numbers to the third case. Okay, so here we are assuming all the k's are real numbers. No, I'm sorry. We assume first, no, here, sorry. We assume first that all the poles are real numbers. Now, we know from the last lecture that we could find kj. We can find kj by using the formula here, kj. We derived this formula last time already, so I'm not gonna go over it again. So s minus pj times xs, and then after you multiply xs with x minus pj, you substitute s with pj. Okay, so this is the formula to use when all the poles are distinct. And this is the easiest case. Now, in the second case, when there are repeated poles, now, after you've determined all the k's and plugged into this formula and take the inverse Laplace transform of x, you'll find that xt will be written as k1 e to the p1 t plus k2 e to the p2 t plus all the way through kn e to the pn t and all multiplied by ut. So this is the general form in the time domain when all the poles are distinct. So you'd have to find all the case first before you can write down this formula, this equation. Now in the second case, there are distinct poles. Oh, I'm sorry. There are repeated poles. Now we suppose that P2 is repeated R times. We suppose that P2 is repeated R time. When P2 is repeated R times, then we can write xt, for example, in IE, that is xs equal to some polynomial m, polynomial of s, ms, divided by some polynomial ns, and then s minus p2 to the r. Now this exponent here is because p2 is repeated r times here, right? So we put the exponent here to the s minus p2 to the power of r, right? ms and ns are some polynomials. So in this case, we could write xs equal to k1 times over let me put pole 0 here. Okay, k1 over s minus p1 plus k2 over s minus p2 plus blah 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 times plus k kn divided by s minus pn, and then plus k01 over s minus 0 I need to move them closer because we don't have much space here, and then plus k02 divided by s minus p0 squared plus blah 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 times plus k0r divided by s minus p0 to the rth. Now there are two sections in this equation. The first section here and the second section. Now the first section here, in the first section we assume that all the poles p1 through pn are distinct. So this section is for the distinct poles. Now in the latter section here, this is for p0, which is repeated r times. So Notice that because P0 is repeated r times, we have r terms here, and each term is distinct from each other by the exponent, by the power here. So you see, this is to the power of 1, this is to the power of 2 until to the power of r. So we see that there are terms, which is exactly the number of times pole 0 is repeated. Okay, so r terms here. Okay, and for the distinct poles, we just write down as usual, just as in the first case. Now, K1 and Kn could be found easily. Remember, K1 through Kn are corresponding to the distinct poles. Pn using Kj equal to S minus Pj times Xs, and then plug in S by Pj, okay, where J is 1 through N. Now this is for the distinct pole. Now for the repeated pole, for K01, K02 until K0R, and these are corresponding to the repeat poles P0. Okay, the method to find this case will be trickier, and we use K0J, right, equal to 1 over R minus J factorial, and then the derivative R minus J times with respect to S. We take the derivative of S minus P0 to the R times XS, R minus J times, and then after the differentiation we plug in S as P0. So this is the formula to find K0J where the poles are repeated. Oops, sorry. Okay, so this is for the repeated poles. This is for this section. For this section, we are focusing on this section here to find K's that corresponds to the repeated pole. Now to find K that corresponds to the distinct poles here, we use this formula, and this is for the green ones. Okay. This formula is quite complex to remember, to memorize. So, but in general, we don't usually use this formula. So in general, not in general, usually we do not use this formula. There actually, I want to say, I guess what I want to say is there is another method to find K0J. Okay, and that begins with, first you have to find K0R. K0R is easy. You don't have to differentiate anything. Just plug in S minus P0 to the R times XS, and then plug in S as P0, and then you can find K0R. Now for K01, K02 until K0R minus 1, we plug in K1 through Kn as well as K0R to this equation. Okay, to this equation. Let's say I'm gonna make it equation 1. Okay, I'm gonna make it equation 1 to equation 1. Then we carry out the algebra and compare the coefficients of s to the k, s to the j, to those in XS, right? And then we could determine K's. Now I'm gonna give you an example of how to do this method, okay, which might be easier. So let's look at this example. Okay, let's look at this example. We have a function hs that is written as s plus 1 divided by s times s plus 3 squared. So when you look at this function, the first thing you have to do is you have to determine where the zeros are, where the poles are. So here when you look at this, you see that there are 1 0. Okay, 1 0, and that 0, which I write down as z1, is at minus 1. And there are 3 poles. There are 3 poles. The first pole is at 0, and the second and third is at minus 3. So 3 poles. Now you see that these 2 poles are repeated. How many times are they repeated? 2 times. Okay, the pole at minus 3 is repeated 2 times. So, because they are repeated 2 times, we can write down hs in this form. Okay, so we have k1 over s, which is corresponding to the first pole. Now, as for the repeated pole at minus 3, we need 2 terms, right? The number of terms here, which is 2, is equal to the number of repetition of P2 and P3, which is also 2. So we need 2 terms. And the first term, denominator of the first term is s plus 3. Okay, that corresponds to s plus 3 here. And the second term is s plus 3 squared. And because we have two repetitions, we end here at 2. Okay. Now the rest of the task is to find the values k1, beta 1, and beta 2. We need to find k1, beta 1, and beta 2. Now, as I said earlier, k1 corresponds to the pole that is not repeating. So to find k1 is easy. You multiply s here to hs. Okay, and once after you've multiplied them, you plug in s equal to 0. Why s equal to 0 here? Because the first pole is at 0, so you plug in the s equal to the first pole. So let's do it. So k1 is s times sh, and plug in s equal to 0, but hs is this guy, right? So when you multiply by s, this term will be dropped, so you are left with s plus 1 divided by s plus 3 squared, and then plug in s equal to 0. Okay, so I guess this is 1 over 9. I guess this is not correct. This should be 1 over 9. Sorry, there's a mistake here. 1 over 9. Because when you plug in s equal to 0 here, you got 3 squared, which is 9, and 0 plus 1 is 1, so 1 over 9. So that is k1. Now, the next one that is easier to find will be beta 2. Beta 2 is s plus 3 squared times hs, and then plug in s as minus 3. Remember, we can find this term and this term, right? We could find the first and last term, as I said earlier here. We could find k. This is the k for non-repeated pole. Sorry. Yeah, here. We could find the last one here, the last one. Okay, and this is the last one. This is the last one. But we cannot find beta 1 using this formula. No, we have to differentiate, as you have seen. So when you multiply hs by s plus 3 squared, what you're gonna get is you're gonna get s plus 1 over s. So I have s plus 1 over s, and then we need to plug in minus 3 to s. So we have minus 2 over minus 3, that is 2/3. So beta 2 is 2/3. Now once we have k1 and beta 2, the rest of the job is to find beta 1 here. Now to find beta 1, you have two options. Either you differentiate using this formula, okay? Either you differentiate using this formula, or you do the algebra. Okay, so I'm gonna do method 1 by using differentiation. Use the formula. So beta 1 will be 1 over, now in this case r is 2 and j is 1, so 2 minus 1 factorial. Differentiate 1 time with respect to s, and we have s plus 3 squared hs. After the differentiation, I plug in s as minus 3. So 2 minus 1 factorial is just 1 factorial, which is nothing, and it is just 1. So I have derivative with respect to s, and s plus 1 divided by s. And then I plug in s as minus 3. Now you have to differentiate it. So I have equal to s minus s plus 1 divided by s squared. Remember, d of u over v is v du minus u dv over v squared. Okay, so u here is s plus 1. So v here, du is s plus 1 with respect to s is 1, right? Minus u, so u dv, okay, divided by v squared. So we have, and then plug in s as minus 3. So we have minus 1 over 9. That is beta 1. Now we have all the ingredients. Another method 2, use algebra. To use algebra in method 2, we plug in k1 as well as beta 2 into this formula, into this equation. So hs k1 was 19 over s, okay, and beta 1 over s plus 3, and beta 2 was 2/3 over s plus 3 squared. But we know hs is this, right? S plus 1 over s times s plus 3 squared. We know that. Now, our job is to combine these terms and then compare the coefficients between them. So I'm going to combine these 3 terms into one big term. The left-hand side would be s times s plus 3 squared, and the first term would be 1 over 9 s plus 3 squared. The second term would be beta 1 times s plus 3. S times s plus 3. I have to be careful here. And the third term is 2/3 s. Okay, and equal to s plus 1 divided by s times s plus 3 squared. Now, I'm going to ignore the denominator because they're equal, so I'm going to focus on the numerator. Okay, as for the numerator, the first term would be s squared plus 6s plus 9. And the second term will be beta 1 s squared plus 3 beta 1 s. And the third would be 2/3 s. And I know that has to be equal to s plus 1. Okay, now I group s squared together. I'm going to have beta 1 plus 1/9 times s squared. Now I'm going to group s together as well. So I have 6/9 plus 2/3. Okay, 6/9 plus 2/3 is 6/9 plus 2/3 plus 3 beta 1 s. Okay, and plus 1 equal to s plus 1. Now I can compare the coefficients. I see 1 is equal to 1. That is checked. And I know that because on the right hand side there is no s squared, right? So this term has to be equal to 0. So I know that beta 1 plus 1/9 has to be equal to 0. And I also know that 3 beta 1 plus 6/9 plus 2/3 has to be equal to 1. Okay, now this gives me, from here, this gives me beta 1 equal to minus 1/9, as we had earlier. See, beta 1 is minus 1/9, beta 1 is minus 1/9. So the results are consistent with each other. Now, what about this one? They better be equal. It's better equal to here. So, here, actually, we don't need this because we already know that beta 1 is minus 1/9, but this is for fun, actually, for confirmation. Now, if you do the calculation, you're going to see that beta 1 is 1 minus 4/3 divided by 3. That is minus 1/9 as well. So all the results are consistent with each other, so we're fine. So either method gives me beta 1 equal to minus 1/9. So I have all the ingredients here. So I have K1 equal to 1/9, beta 1 equal to minus 1/9, and beta 2 equal to 2/3, right? Yeah, 2/3. So that means HS, I can write down HS now, 1/9 over S minus 1/9 over S plus 3 plus 2/3 over S plus 3 squared. Now from here, okay, we take the inverse Laplace transform of each term. I'm not gonna get here, this one here, right? So when you take the inverse Laplace transform of each term, you're gonna get this. By look at the table, you're gonna get this. So this is your answer, your solution. When there are poles that are repeated, when there are repeated poles. Okay, inverse Laplace transform. All right. Okay, any question, please? So, in conclusion, when there are repeated poles, you have two options. First is to use the formula. This is the first method. This is the first method, using the formula. Second, using the algebra. I think either one is complicated. Okay, using the algebra is more complicated, but it's easier to manipulate because you don't have to differentiate anything. Just use the good old algebra. But if you use the formula, it is less complicated, but you have to do the differentiation. So it's up to you which method to use. All right, I'm presenting two methods, but in general, we tend towards this method because in general, we don't. It is very, very hard to remember. It is very hard to remember this formula. Okay. All right. Now, let's go to the third case. Now, let's look at the case where there are poles that are complex numbers. The thing that you have to know is when there are complex poles, the complex poles will come in as conjugate pairs. So this is important. When a pole is a complex number, it will come in conjugate pairs. You have to take this into account. Now, what do I mean by conjugate pairs? For example, if you find that there is a pole at sigma plus j omega, you know immediately that there will be another pole at sigma minus j omega. Okay? By conjugate pairs, we mean one is j omega, the other would be minus j omega. These are called conjugate pairs. The imaginary parts are inverse to each other, are negative to each other. The signs are opposite. So now let's say that pi is a complex pole. Okay, so there would be another p, which is pj. We call it pj. That is a conjugate to pi. So if pi is sigma plus j omega, I have pj equal to sigma minus j omega. Remember, they have to be complex conjugate poles. Now, because these two poles are distinct, okay, in case 1, we can write down hs as these two added together plus the rest of the terms, which we don't know. Okay, we are focusing on these two poles only, right? So we could write down this corresponds to the first pole, and this term corresponds to the second pole, which is the complex conjugate to each other. Okay, ki and kj are distinct. Now, you will find that from here, you can find ki and kj using case 1, method 1, right? By multiplying hs by this guy, right? And after you've multiplied them, you plug in s equal to sigma plus j omega, which is the first pole, which is this pole. Now, same goes for kj. Okay, you multiply hs by this guy, right? Once you've multiplied them, you plug in the second pole into s. And when you do this, you will find eventually that ki and kj are complex conjugate to each other. Okay, you can show that these constants, by these constants I mean ki and kj, are complex conjugate to each other. So I have kj equal to ki conjugate. Now I'm gonna write down kj here as ki conjugate. Okay, here. So we have these two terms, and then we add them together. We add these two terms together. When you add these two terms together, you will find that the result will be as plus b divided by s minus sigma plus omega squared. Now it turns out that here now a and b are real numbers now. For example, I'm gonna give you an example momentarily. So we can write down hs as here. Now the next step is to find the inverse Laplace transform of this guy, right? Now to find the inverse Laplace transform of this guy, we look at the table. The closest ones to this guy would be the Laplace transform of e to the sigma t cosine omega 0 t, and this is equal to s minus sigma over s minus sigma squared plus omega 0 squared. and the inverse Laplace the Laplace transform of e to the sigma t sine, which is omega 0 divided by the same denominator. So our job is to manipulate this into these two. Okay, we need to break this guy somehow. We need to break this guy into these two forms so that we'll be able to take the inverse Laplace transform and get these two. Now to do that, now if you do that, you find that and you had taken the inverse Laplace transform, you find that the inverse Laplace transform of this term can be written as these two terms added together, and that would be the inverse Laplace transform of h. And the capital A is the letter A here, the value A here, and the capital B is A sigma plus B small b divided by omega. Okay, omega is this, is the imaginary part of the pole. Okay, so let's look at an example. It might look complicated, but if you look at the example, it's actually easy, not that complicated. Now, so look at this example. Now let's look at the denominator. From we want to find the roots of this equation. Okay, to find the root of this equation, you can use the formula here. You could use the formula and see that the roots are minus 3 plus minus j4. So you see the poles are complex numbers because there is the term j here. So I know from here that P1 is minus 3 plus j4 and P2 is minus 3 minus j4. Notice that they come in conjugate pairs, right? One is minus 3 plus j4, the other is minus 3 minus j4, so they are conjugate to each other. Okay, so when we have this, after we have this, I pick P1 as our principal pole. Okay, you could pick either one. You could pick P2. The result will always be the same. I am now just simply picking P1. So I have sigma, which is the real part of P1, and it is minus 3. And omega is the imaginary part of P1, and it is 4. Okay, and so I could use this formula. That Hs equal to 2s plus 1 divided by s squared plus 6s plus 25. I want to rearrange this. I know that I have to rearrange it. I have to find this. I have to write it into this form, right? The denominator is the perfect square. Okay, is in a perfect square, so I have to write down the denominator in the perfect square. So I have 2s plus 1 divided by s plus 3 squared. and then plus 4 squared. Okay, here this is sigma. Okay, sigma. See here, sigma, right? So sigma goes here, and this is omega goes here, and the numerator is 2s plus 1. So here I know that a is 2, b is 1. Okay, see, a is the coefficient of s, b is the coefficient of s to the 0. a is the coefficient of s, b is a constant. So a is 2, b is 1. And then I could use this formula here. So I can calculate capital A. So the capital A is equal to A, which is 2, and capital B is equal to sigma A plus B over omega. Sigma A plus small b over omega. But sigma is minus 3. A is 2. B is 1. Omega is 4. So the big B is minus 5 over 4. Sorry. Minus 5 over 4. Okay? And so I have this. I plug into this, right? Capital A goes here, which is 2, right? Capital A is 2, goes here. And this term is sigma, which is minus 3. So minus 3 goes here. Omega is 4. 4 goes here. Okay? And capital B, which was minus 5 over 4. So minus 5 over 4 goes here. And omega goes here again. I'm sorry, the sigma goes here again, and omega goes here again. So once I have these 4 guys, I can write down the inverse Laplace transform of H. Now, it turns out that from here, we can combine them, okay? We can combine them into this form using phasors, okay? We can combine them into this form using phasors. Right. You can pull e to the minus 3t out, right? And then you combine 2 and minus 5/4 using phasors. Okay, they are perpendicular to each other, so you use the Pythagoras on them, and you're gonna get square root of 89 over 4, and then the angle between them is 32 degrees. So you can write down HS in this form. Okay. Let's do this. To clarify what I said, I'm gonna give you the detail. Oops, sorry. Here, from here, all right, I can pull e to the minus 3t out, and inside I'm gonna have two square root of 2 squared plus 5/4 squared, okay, minus 5/4 divided by 2 squared plus 5/4 squared. Okay, and I think I should write down cosine of 4t, and I should write down sine of 4t, but I need this. Square root of 2 squared plus 5/4 squared here. Okay, and then, oops, sorry, multiplied by ut. Now, notice that I can write down a right triangle. Okay, this is theta. All right, and this is 2. This is 5/4. This is square root of 2 squared plus 5/4 squared. Okay, so this term is just cosine of theta, and this term is just sine of theta here. So this is equal to e to the minus 3t, and then I have square root 89 over 4. Actually, square root of 89 over 4 e to the minus 3t, and then the inside it would be cosine of 4t cosine of theta, and then minus sine of 4t and sine of theta ut, right? Now theta, if you do the calculation, theta would be 32 degrees. Okay, theta is the arctangent of 5/4 over 2. Now pick up your calculator and you'll find that it is 32 degrees. 32 degrees. So we have square root of 89 over 4 e to the minus 3t cosine of 4t cosine of 32 degrees minus sine of 4t and sine of 32 degrees ut. And we recognize that this is just cosine 4t plus 32 degrees. So we have square root of 89 over 4 e to the minus 3t cosine of 4t plus 32 degrees. Okay, this is what we have here. So I gave you the details of how to reach this. All right, so this is an example of how to find the inverse Laplace transform when there are complex poles. Okay, now you can pause, you can rewind, and if you have any question, you can raise your hands and ask. Let me know. Okay. Now, let's look at another example. We have the same HS, but now this function is assumed to be the transfer function of an LTI system. So in this example, we have an LTI system with the transfer function that looks like this. Now we have the unit step signal as the input to this system. So for in other words, we apply unit step signal into this function, into this system. Okay, and we want to determine the zero state response when the input is the unit step signal. Now we know that the zero state response ys can be written as the product between the transfer function and xs, okay, where the transfer function is this guy. And what is xs? Xs is the Laplace transform of the unit step signal, and the Laplace transform of u, because it's a unit step, right? We know from the table that is 1 over s, so 1 over s written here. So we plug in 1 over s to here, and we plug in hs to here, and we're gonna get, we're gonna get this. We get this. Now, because we need to find the time domain of this, so we need to do the inverse Laplace transform of this. And you see here, there are 1, 0. Okay, 1, 0, which is the same 0, and that is minus 0.5. Actually, sorry. 0 was, yeah, minus 0.5. Different one. The 0 is minus 0.5 here. I think that actually, well, okay. Yeah, okay, all right. Okay. And there are 3 poles. What are those poles? The first pole is at 0. Okay, that corresponds to this term. And the second pole is exactly the same as the previous example, which are P2 equal to 3 plus J4 and P3 equal to 3 minus J4. Okay, so we know that here these 2 poles are complex numbers and complex conjugates to each other. So the partial fraction of y would be, for P1, this is distinct from the rest and it is real. So I have K1 over S. Now, as for the complex poles, I have AS plus B divided by S minus sigma squared plus omega squared. All right. Now, sigma is minus 3. Oh, sorry. Sigma is what? Sorry, I don't remember. Sigma, oh yeah, minus 3. Minus. Okay, so I know that sigma is minus 3 and omega is 4. So I have, and yeah, okay. K1 over S plus AS plus B divided by S plus 3. I plug in sigma and omega into this, plus 16. Now I have to find K1. K1 is easy because it is distinct from the rest. So I have SYS and then plug in S as 0. Okay. So when I multiply Y by S, I have to drop this, right? So when S is 0, I have 1 over 25. So K1 is 1 over 25. All right. And then A here is 2. No, A is not 2. Sorry. Now I have to find A and B. Okay. But I have to write down YS as 1 over 25 divided by S plus AS plus B divided by S plus 3 squared plus 16. Now I have to find A and B. Now how do we find A and B? It's not easy. Okay, so we need to do the algebra to find A and B. To find, there is no formula. To find A and B, we do algebra. So I'm gonna combine these two together. Okay, so when I combine them together, I have 1 over 25 s plus 3 squared plus 16. Okay, and plus as squared plus bs. And I know that this has to be equal to 2s plus 1. So it has to be equal to 2s plus 1. Remember, this is 2s plus 1, right? And this is the numerator of the right hand side. So it has to be equal to 2s plus 1. Now, on the left hand side, I have 1 over 25. Inside is s squared plus 6s plus 25 plus as squared plus bs equal to 2s plus 1. Now I group all the similar terms together. I have a plus 1 over 25 s squared, and then plus b plus 6 over 25. Okay, s and plus 1 is equal to 2s plus 1. So from here, I know that the coefficient of s squared has to be 0 because the right hand side doesn't have s squared. So I know that a plus 1 over 25 has to be 0. That means a is equal to minus 1 over 25. And I know that b plus 6 over 25 has to be equal to 1. Has to be equal to 2, sorry. So this is equal to 2. So that means that b is equal to 44 over 25. So I plug it in, plug these two things back to ys. So I have ys now equal to 1 over 25. Sorry, I'm gonna pull 1 over 25 out. I'm gonna have 1 over s minus s plus 44 plus minus s plus 44 divided by s plus 3 squared plus 16. And now I can use my formula. Okay, so I have yt. This guy is ut, right? So it's equal to 1 over 25. The first term is ut. As for this one, I use this formula here. Where here? Okay, a and b. Now I have to find a and b, right? Let's use this. I'm just gonna copy them. Okay, I'm just gonna copy them. Okay, because I don't remember, honestly. Plus a. What is a? A is minus a. A is a. Okay, the capital A is the small a, which is found to be minus 1 over 25. So minus 1 over 25. Yeah, actually I need this. I need to do this. Sorry. 1 over 25 over s. I should write it now like this. Minus one over 25 s plus 44 over 25 divided by this guy here. So yt is 1 over 25 ut. Okay, and plus a is minus 1 over 25, so minus 1 over 25 e to the minus 3t cosine of 4t ut. Now b, what is b? A sigma plus small b divided by omega. So I have to find b. Sorry, b is a sigma plus b over omega, and that would be minus 1 over 25 times sigma, which is minus 3, plus b, which is 44 over 25 divided by omega, which is 4. So I have 47 over 24 as b. 47 over 100. That is b. Okay, so I have plus 47 over 4 times 25 cosine, sine of 40 ut. Okay, and now I can erase this. Don't need this anymore. I should write down a is equal to y. A is equal to 1 over minus 1 over 25. A is this guy. And then I'm gonna pull minus 1 over 25 e to the minus 3t out. Oh, I forgot this term. E to the minus 3t here. So I have 1 over 25. 1 over 25. 1 minus e to the minus 3t cosine of 4t and minus 47 over 4 sine of 4t ut. Okay, here. And then I have to combine these two together. Actually, you can answer this. It's okay. But I want to combine these two together. Now, oops, sorry. Now, cosine of 40 minus 47 over 4 sine of 4t. Okay, this is equal to square root of 1 plus 47 over 4 squared The inside is 1 over root 1 plus 47 over 4 squared cosine of 4t minus 47 over 4 over square root of 1 plus 47 over 4 squared sine of 4t. And write down the triangle. Okay, this is theta. This is 1. This is 47 over 4. This is square root of 1 plus 47 over 4 squared. So I have, actually, what do I have? 2225. I want to use a calculator. Where's my calculator? 16 plus 47 squared. 2225 over 4. Okay, 2225 over 4. I think I should have this 2225 over 4. Yeah, 2225 over 4. And the inside parentheses would be cosine of 4t cosine of theta minus sine of 4t sine of theta. Yeah. So that is root of 2225 over 4 cosine of 4t. Now, what is theta? Theta is arctangent of 47 over 4. Arctangent of 47 over 4. That's 85 degrees. 85 degrees. 85.2 something. So 85 degrees. So here, all right, I can replace it with this guy. So I'm gonna have, this is my yt. Okay, so yt is this. So 1 over 25, 1 minus square root 2225 over 4 e to the minus 3t cosine of 4t plus 85 degrees. And that would be our zero state response from this system when the input is the unit step signal. Okay, here I think I missed the term 4. Here I missed the term 4. I'm sorry about that. I should have the term 4 here. All right. Okay, so yeah, so this is the complex pole case, and you see it is quite complicated. Okay, all right. Now the next topic would be the determination of the stability using the transfer function. It turns out that stability of an LTI system can be determined by looking at the transfer function. To be specific, by looking at the poles of the transfer function. Look at the poles, and you will be able to determine whether the system, the LTI system, is stable or not. Now, the detail is that for the system to be stable, all the poles would have to be on the left-hand side of the complex plane. That is, all the poles would have to have negative real parts. Okay, this is the condition for an LTI system to be stable. Look at the poles. Okay, just look at the poles. For example, a system is described by this transfer function, and the poles, how many poles are there? 3 poles. The first pole is at -3. The second pole is at -3 plus J4, and the third pole is at -3 minus J4. Now, if you plot it on the complex plane, the horizontal is the real part, and the vertical is the imaginary part. Okay, the first pole is at -3. The second pole is at -3 plus J4. The third is at -3 minus J4. You see, all of them are on the left-hand side of the complex plane, the left-hand side. They all have negative real parts, so the system is stable. Now, let's look at this. Now, you see 3 poles. The first is at 1. The second is -3 plus J4. And the third is -3 minus J4. Now, you see, there is one pole that is on the right-hand side. P1 is here, whereas P2 and P3 are here. So, because of this guy, this system is not stable. So the system is not stable because of P1. Here, this is on the right-hand side, right? So the system is not stable. Okay? All right. So this is all I wanted to say today. I don't want to go into another topic. You guys are still here? How many people? Yes. All right. You have any question? I have recorded this lecture already, so I'm gonna post it on YouTube. And if you want to stop when you look at the clip on YouTube, if there's something you don't understand, you can stop and pause and then rewind, go back, word, and look at it again. But now, you have any question to ask? Pumipat, you here? Pumipat? Who's here? Napat? No one? Yeah, are you have any question? Who's that? Pumipat, right?
Napat.
Napat, you have any question, Napat?
No.
Okay, if you have questions, look at the YouTube. Okay, I'm gonna post the clip. All right, so if you don't have any question, I'm gonna call it a day and see you again on Tuesday, as usual in class. All right?
Okay.
Okay, bye bye. See you guys.
Bye. Thank you.
Bye bye.
สวัสดีครับอาจารย์
สวัสดีครับ